Right. Good afternoon. Today is 5th of November 2020. Today is week 13 on a Thursday, and we are doing our last tutorial online. So I have some announcement to make. First is that please remember that we have quiz 4 on week 14. This is the location. You'll be at LT7 and LT8 respectively. So please go to the correct location for your group. It'll be again a 55 minutes quiz. So please arrive promptly. Right, you'll be again closed book. And in the announcement I made, I have already highlighted to you the scope. So you can ignore everything else except tutorial 7 and tutorial 8 in these questions, where I mean this question is only not doing these questions, but all the theories associated with these questions. Okay, so you have to do tutorial 7 or and you have to do tutorial 8, question 1, 7, 10. Now you realize that I put up the videos of question 1, 7, 10, and to do justice to the course, I've added a pendant to the questions. So the questions given here are incomplete. So please go to the videos to see the complete, what do you call that, questions. So maybe I would highlight now so that you guys can see the questions that have been modified. So question 1, 7, and 10. So let me pull this here. Looking at my screen, mumbling to myself because I'm not. I think I'm sharing my screen now. Okay, so let's go through what is new here. In question 1, this was the original question, and then I've added a pendant to it. So you have to do the additional questions, which is highlighted in the recorded video. Question 1, question 7. So this is the additional questions of question number 7, and question number 10. In question number 10, this is the additional question. Okay, so question 1, 7, and 10 all have additional questions, and you can see, watch the videos. So let me pull out the videos for you. So go to our linear algebra YouTube link and go to tutorial 8. You will see that I have put question 1, then bracket 6 means the part 6, the small little part 6 of question 1, number 7, question 7 different parts. And then everything is here. Question 1, question 7, and question 10. Question 10 would the additional questions as well. Okay, so you have to go through all these, and you'll realize that among the tutorial 7 and tutorial 8, one part will come from these questions in tutorial, and the other part will come from tutorial 7. So you need to do both parts to get all the marks. Okay, so that it means that I have given you enough tutorials, as in tutorial recordings, to do all the questions. So what I'm going to do today instead is to go through SVD, and it'll be a small quick introduction to SVD, pseudo-inverse, and then we'll do the, well, I won't do the tutorial, I'll just go through it very quickly. Okay, right, so maybe before I start, I'm going to pause now to, okay, so we are back. What I'm going to do for the next few minutes is to go through very quickly what is SVD, this slide, 8.4.1, and the pseudo-inverse slides. What we now know is that eigenvalue can decompose a matrix, but it can only decompose a square matrix. We have realized that decomposing a matrix A into a square into splitter parts are very and it allows us to do many things. However, when it comes to a rectangle matrix, we know that we cannot do eigen decomposition. Instead, we can do a decomposition that looks like this. We have A decomposed into three matrices. Let's compare them. This is the eigenvector. This is the eigenvalue. This is the inverse of the eigenvector. And this is square. On the right-hand side, we have a rectangle matrix. Of course, a square matrix can also be used, but typically we use it for rectangle. This is the left singular vector. This is the singular value. And this is the right singular vector. Okay, so basically SVD, singular value decomposition, decomposes a rectangle matrix into three matrices, and these are their names. This is Richard Brunton, and he does a much better job. Okay, and I'm not ashamed to say he does a much better job describing SVD than I ever can. All right, so what I would suggest to you is to look at this, and then it will come out understanding that we have three matrices, and it looks like this. Okay, once you have understood this in our course and quiz, at least you only need to know that A breaks down into three matrices, and these three matrices have these names, and these three matrices, when multiplied this way, reconstruct A, which is amazing. Okay, especially because D is a diagonal matrix. And not only amazing, more amazingly is also U transpose U is identity. U transpose is identity. That means U is an orthogonal matrix, and V as well is an orthogonal matrix. But there are some catch here. Later on, you will see that actually sometimes we will not use all the columns of U, then U transpose U or U transpose to become identity. But we'll come to that in a couple of minutes. All right. How does it look like? Let's now look at the size of the matrices. A is m by n. Okay, so we like a tall, thin rectangular matrix, and this is what is typical of data scientists. We have many examples. So if imagine if each row is one example, and then we have many examples of some things. That's one way to fix out. And U is an m by m matrix. Now in this, please remember that when we do U to be an m by m matrix, it means this is a square matrix. This only happens when we use a full SVD decomposition. Versus there is something called an economy SVD decomposition, which will not get you m by m. Okay, I'll come to, but let's say that an A can be decomposed into U, which is an m by m. Now, you'll be thinking n is less than m. So where, so, so, so what about these guys, right? Let's say this will be, if this is n of them, you'll be thinking, what information, you know, if these are the columns of A, the first n of them will be the columns of A space in U. So what is this shaded region, you know? So in fact, this will be actually, if you read it carefully, it is the orthogonal complement of the column space of A. Yeah, so it's just a mouthful. Huh? Orthogonal complement means nothing to do with the column space of A. Okay, it's complement. So U is actually producing Rm, meaning the whole space of M, Rm. All right, that means we have enough vectors in this U to reconstruct any vectors in Rm. But in fact, in A, we only have n of them. And in n, so I'm going to now shade in pink, is all here. So this guy and these guys are related. They are the same space. While now the dark blue guy, this guy are the orthogonal complement of the column space of A. So in fact, that blue guy, you know, is something we constructed out of constructed out. It didn't come from A. It just come from, outside A. Okay. Now, what about D? In the full SVD decomposition, D is M by N. You realize that all these are zero. This zero is associated with these zeros here because you realize that since A is constructed by only the first N column, these are the N column, therefore only the diagonal first N entries are important. After that, for the blue guy, we are going to multiply by 0 so that they are not going to be activated or used. Finally, we have VT. And to get the correct size, which is M by M, M by N, the guy must be N by N. So this is the full SVD. Now, when I first studied SVD, I had a huge problem, guys. You realize that to reconstruct, A is equals to U, multiplied by D, multiplied by V transpose. Okay, so this little symbol is the transpose. But when you use SVD, using MATLAB or using Python or whatever, V is written as a column matrix. Okay, so is U is a column matrix. So U is used directly. D is also written as a square matrix. Oh, sorry, M by M matrix. So U and D is used as is written, but V, you must transpose it to use it. So it's A equals to U times D times V transpose. Let us see an example in MATLAB. Oops, where's my MATLAB? Okay. All right. So I'm going to step, then you're going to see. The first thing I do is to construct A. A is 1, 2, semicolon, 1, 2, semicolon, 1, 2. So what is A? I'm going to run this. And so this is A. A is nothing but a matrix with 2 columns. Not only that, it's a matrix with 2 dependent columns. The first column times 2 is the second column. So M is 3 because there are 3 rows. N is 2 because there are 2 columns. What is the rank, guys? So you haven't played with the rank yet, but remember the rank of a matrix means how many independent rows or columns there are. And in this case, the answer is R is 1. So among this matrix is rank 1. That means there's only one column that is exciting or one row that is exciting. The rest are just dependent values of it. Okay. All right. So now I keep on going, and then immediately I should bring my SVD out. So let's bring my SVD out. Right. Oops. Let's run again. So I've just run what is A again. I'll show you A again. A is 1, 2, 1, 2, 1, 2. What is UDV equals to SVD A, meaning that I call the SVD of MATLAB to decompose A into 3 matrices, U, D, and V, and then I will show it to you. So remember what I told you U is a 3 by 3 matrix. So there you go. It's a 3 by 3 matrices. D is a diagonal matrix. So there, well, let me be very correct. D is a 3 by 2 matrix. Only the diagonal elements of D are non-zero. Then you'll be telling me, hey, there's only one non-zero. The other guy is a 0 value. And this is a 0 value because rank is only 1. Okay, we're counting the number of non-zero entry in D, there's only 1. So this is correct. And finally, V is a 2 by 2. Let's go down. Yep. So now let's play with the properties of U. Remember, U is supposed to be an orthogonal matrix. What is the orthogonal matrix? It means U times U transpose is I. Oops, okay, correct. U transpose times U, also I. Yes, correct. So U is an orthogonal matrix. What about V? Same. V times V transpose, I. V transpose times V, I. Great. So now we have seen what is U, D, and V. So how to get A? So let's see what's A again. A is these two columns. U times V, U times D times, okay? So please, it's V transpose, okay? U times D times V transpose. And if this answer is correct, it's the same. Okay, great. So many beginners will make this mistake. All right, this is a mistake people will make. It's UD times V. This is wrong. You come out rubbish. Okay. So this is the correct answer. All right, so I have decomposed. Now, if some of you is going to ask me, what is an economy size SVD? All right, let's go and get the economy size SVD for you. So an economy SVD will be here. By putting a 0 here, this is a full SVD, I should say. Okay, let's let me. Okay. So what's the difference, guys? I'm going to do SVD A, comma 0. So please go and do help SVD, and you will see what does this 0 parameter do. This 0 parameter will basically, okay, let's run this code. Then you will be comparing U and UE. It becomes a 3 by 2 matrix compared to U. Compare UE. So what's the difference, guys? One column is missing. The orthogonal complement of the column space of A is missing. Or in English, it says the last few columns are missing because only the first n columns are important. Okay. What about V? V compared to VE? Same. What about D compared to DE? Same. So the only thing difference is in the economy SVD, the U is not the square matrix U. That's all. Okay, so we've gotten that out of the way. And then, all right. So we now can go to pseudo-inverse. Okay, so in the question, let's go and see our pseudo-inverse. In the tutorial question, and this is important, guys. Please read 8.4.4. Pseudo-inverse. Now, if you do MATLAB, it is nothing but this command. And of course, if you're an engineer, then you want to pass something called tolerance in it. But well, let's not go there. Watch this video to get the pseudo-inverse, and I will do it very quickly here. A equals to this. The pseudo-inverse of A is A plus, as opposed to A minus. This guy is the inverse of A. A plus, the pseudo-inverse of A. Okay, now what is A plus? Okay, A plus, then you'll realize that something interesting and exciting happened. V transpose was last in A, it becomes the first guy. It was transposed, but here don't have transpose. Here was sigma, but here is the inverse of the sigma. What is the inverse of a sigma? Here, the sigma is a diagonal matrix. The inverse of a diagonal matrix is nothing but all the diagonal elements reciprocated. Finish. U is U transpose. Then there's a huge relationship, right, between these guys. Because remember something, remember that, what was the thing? Yeah, in fact, yeah, Brunton also does that. If, remember V and V transpose V is equals to I, sigma and sigma minus 1 is I. And if we are doing full decomposition, U and U transpose is also I. So what is this? A plus equals to I. So doesn't it behave very much like a inverse? And yes, it does. So the confusion comes when you're not using full size decomposition of U, or confusion comes when you're having problems with rank R. Okay. All right. So we figure out that pseudo inverse and inverse is very, very close to each other. So let's take a look at the pseudo inverse. First, you'll be thinking to yourself, how would I get a pseudo inverse of a rectangle matrix, right? What would it even look like? Because a square matrix inverse is another square matrix. What about a pseudo inverse? What does it look like? All right, let's see. So I am now here. Okay, let's cancel this first. db quit. Now let us run and let us continue, and then I'm going to run this line called AP, which is a short form for A pseudo inverse, and then this is the pseudo inverse. So the pseudo inverse of a 3 by 2 matrix is a 2 by 3 matrix. So let's figure this out. So if this guy is a 3 by 2 matrix, this guy is a 2 by 3 matrix. And now we have A plus. So this guy is a 3 by 2. This guy is a 2 by 3. What do I get? A times AP. Then you say there is no identity, right, guys? But well, we'll come to that. So I'm going to check these few things for you. A times AP. But wait, A times AP times A, what do you think will happen, right? Now, if A times AP is identity, then A will come out. But you say A times AP is not identity. Some funny numbers. Whoa, A times AP times A gives me back A. So A times AP behaves like an identity matrix in this particular case. Something strange is going on here. So to see the properties, please go to 8.4.4, and we are back to Brunton. All right, guys, where am I? Oops. Yep. So we are talking about this property here. Okay, you realize that a pseudo inverse doesn't give identity unless there are very special situation, independent column. But our little a wasn't independent column, so our friend didn't come out. Okay, but something else came out. But all these properties must come out. A, so this guy must behave like identity, right? So, okay, it did. What about this guy? See? So this also try to behave like identity. So A plus times A plus should be A plus. Okay, let's try. So check number 2. A plus times A plus should be A plus. So this is check 2, and this is A plus, and the answer is, oh man, same. Wonderful, isn't it? Yeah. So I check 1 and check 2, I got it. So it acts like a weak inverse, it says. All right, I wouldn't do the, then of course you'll be thinking to yourself, what does A times A plus means and A plus times A means, yeah? So I have check number 3 and check number 4, okay? and then I run. And in fact, I'm going to tell you the answer. A times A plus, where am I? Oh, man. Okay, uh, sorry, check two. Okay, all right, never mind. What I'm going to do is this. A times A plus will give you the projection matrix of a column space, and A plus times A will give you the projection matrix of the row place. A times A plus times A, and you figure out that these are the projection matrix. Right, finally, in the tutorial question, and I'm asking you to do this slide, and he says, use the SVD. Here, the reduced SVD means the economy SVD. Find out the pseudo inverse of A. Oh, sorry. Okay, guys, if I'm mumbling to myself, it's because I'm looking at my iPad and I'm writing on my iPad without realizing that it's not being projected. Okay, so shout at me. Okay, now let me try to get the correct. Okay, so let me show you the tutorial questions first, and then you will understand what am I asking for. Okay, the easy stuff first. In 18, I tell you that A is square and invertible, and find the inverse of A using SVD. So U is equals to, sorry, not U. The answer is A equals to U sigma V transpose. A is square, so this is n by n. This is n by n, n by n, n by n. See, so it's quite trivial. Not only that, U transpose equals to I, U transpose U equals to I, V transpose equals to I, V transpose V equals to I. Not only that, sigma equals to diagonal, and all entries are non-zero. Why? Because this is given to us, invertible. Okay, so we have all this property, and what is A plus? A plus is defined as V sigma minus 1 U transpose, and this will be equals to the inverse of A. So when we have this condition, A is a square and invertible, the pseudo inverse and the inverse will agree. Okay, so it's not magical, it's just a very, you will realize that pseudo inverse is a very powerful inverse. It can deal with square, and it can deal with non-square, and not only it can deal with non-square, it can deal with rectangle that has dependent column. So it is like a Superman, yeah, the SVD and the pseudo inverse. All right, so let's prove to ourselves why this is so, because you'll realize that. Let's try A plus times A. What is A plus times A? We take this guy, V sigma minus 1 U transpose, and then we take this guy, U sigma V. Let's cancel, this guy cancel, this guy cancel. Of course, it's I. What about the other way around? A times A plus. So this is U sigma V transpose, and this guy is, so this guy, wait, let me get this right. This guy is uh, V sigma U transpose. So now this guy cancels, and this guy cancels. So we figure out that when A is square and invertible, the pseudo inverse becomes the inverse because of all these properties. Now, this is more exciting. The second part is much, much more exciting for you and me. First, m is greater than n. I'm giving you a m by n, tall and thin. Not only tall and thin, I'm giving you r less than n. So I'm giving you maybe one column and two column. For example, n is equals to 2, but the r is equals to 1. So implying column 1 is proportional to column 2. Our example of 1, 1, 1, 2, 2, 2. Right? So this is 3 by 2, but yet our friend rank is equals to 1. So this is the problem we are going to do and how to find the pseudo inverse. Okay. So let me wrap this up. And then we are going to do a concrete example, and you see that my MATLAB agrees with my intuition and my theory, which is okay. Let's write it in full. A is a 3 by 2 U sigma V transpose. Let me let's get a full matrix. Okay, let's do a full decomposition. So U will be a 3 by 3. So let's call this U1, U2, U3. This is a 3 by 3 matrix. That means each of these U is a R3 element. Our friend sigma is this guy. Oops. So I'm going to call him sigma 1, 1, 0. What about this value? What about this value? Okay, you realize that because I'm rank 1, okay, rank 1. Where's my rank 1? Here. I'm rank 1. Then only one guy, one of the, what do you call it? One of the, I'm only going to count one non-zero singular value. This guy will be 0 and this guy will be 0. Okay, and finally V transpose will be V1, V1. Okay, transpose, V2, sorry, V2. Okay, now you realize that all these zeros here basically will remove this guy, because when you're multiplying zeros, you're actually removing columns in U, you're removing rows in V. So you are in fact doing nothing but U1 multiplied by sigma 1, 1 multiplied by V1 transpose. Okay? Did I get my matrix? So this guy is 3 by 1. This guy is 1 by 1. This guy is 1 by 2. Answer is a 3 by 2 matrix. And this guy would be equals to, what am I doing? Yep, A. Okay, so I'm still getting A. I haven't get the pseudo inverse of A. Let me show you my MATLAB code. I'm going to reconstruct, okay? I'm going to reconstruct A. I'm going to reconstruct A test equals to U times D times V transpose. Did I get it right? And I'm only going to use R equals to 1. Only one, what do you call that? I'm going to use 1. Do I have U? Yes. So I'm going to do this. So let me get A test out first to see I'm right. Sanity check. Yes. So I can reconstruct A using only rank R. Okay. Now, finally, I want to get the pseudo inverse. Okay, let's get the pseudo inverse. The pseudo inverse of A, which is A plus, is equals to V sigma minus 1 U transpose. But if I am only using rank R, I must use VR sigma R minus 1 UR transpose. What does this mean? It means the first R column of V. What does this mean? The first R column of U. And here means the first R diagonal entry. Okay, so if you want to see the code, which is much easier to understand, I am using here the first R column of V. Here is the inverse of D. For the first R entries of D, 1 dot divided by D, 1 colon R, 1 colon R. And finally, the first R column of U transpose. Let's see the answer. And let's check that it is P inverse as well. P inverse of A, and it is the correct answer. Okay, so let's go back to the theory again. And I am doing equation number 10 here. Oh, sorry, I'm mumbling to myself again. Okay, so with that, then the last question of the tutorial 8 question 10 has been answered. You must practice it by yourself to get a hand of it. So I'm now going to pause and then I'm just going to chat with you guys.